Okay, the next unit that we're working on is going to be dealing with functions. So we're going to be looking at functions, at finding domain and range, doing difference quotients, combining functions and composing them. But it all depends on you having a really good understanding of what is a function, the gist of domain and range, and then you need to really make sense of function notation. Okay, so the first video I'm going to do is just dealing with function basics. Okay, so the handouts that I'm going to be using are in the folder dealing with functions in that course handouts and videos area in Blackboard. Okay, all right, so let's go ahead and talk through some of the function basics. First off, we've dealt with a lot of equations in two variables. We've dealt with things like 2x plus y equals 13. We've looked at things like y equals square root of x minus 5 and things like x squared plus y squared equals 9. All of these are relations in two variables. Any equation in two variables, any set of ordered pairs is a relation. There's not a whole lot special about that. No special properties have to hold true. Okay, but to be a function, there's an additional property that must be met. Okay, a function is going to be a relation in which for each x value, there is only one y value. Okay, for each x, there's only one y. All right, so like the first and the second ones of these are going to be functions. This is a function, and this is a function. But x squared plus y squared equal 9, we'll find out, is not a function. Okay, we'll look at some reasons why in a little bit. All right, what's going on in this next area is I'm looking at the different representations. How can you tell if something's a function if you've got a graph? Okay, or how do you tell if you have a table, or maybe a set of ordered pairs? Okay, what would you need to see for it to be a function? And then the third thing is, what if it's an equation? So what if we're looking at a graph? What if we're looking at a table? What if we're looking at an equation? Those are just three different representations you can use for a relation in two variables. Okay, so if you have a graph, you can see if it's a function. You can see if each x has only one y by using what we call the vertical line test. Vertical line test. Okay, so if there is a place where a vertical line crosses the graph in more than one spot, it is not a function. So for instance, these three examples I was just using. Okay, the first one turns out to be a line. Okay, so number 1 turns out to be a line, looks something like that. Number 2 is a square root, and it would look something like that. And number 3 is a circle. Okay, well, you can't find a vertical line that's going to cross this in more than one spot. The vertical lines are only going to hit it once. Same thing here. Any vertical line is going to only hit the graph once, but on number 3, it's going to hit it in more than one spot. You can find a place where it hits it in more than one spot. So this is the one that's not a function. It doesn't pass the vertical line test. Okay. All right, you can also tell if you don't have a graph, if you have a table or a set of ordered pairs, you can check to see if it's a function by making sure that no two different ordered pairs have the same x. Okay. All right, so you can't have this situation. You can't have an x of 0 going to 3 and an x of 0 going to -3 like it would with that circle right there. Okay. So because this happened, not a function. But when I'm thinking about why that's not a function, I kind of relate it back to the vertical line test. Okay, if we were to plot 0, 3 and 0, -3, they would line up like that above. Oops, that's not where they would be. Let me try that again. Okay. If we were to plot 0, 3 and 0, -3, they would line up above one another. See how they would fail the vertical line test? There would be a vertical line that could hit those points in more than one spot. Okay, so these two ordered pairs would be located above one another. If you have the same x coordinate but different y's, the points are located above one another, and so the relation would fail the vertical line test. So I kind of like just making a connection back to that idea. All right, now there can be two ordered pairs with the same y. Ordered pairs with the same y would line up horizontally. That's okay. That's still a function. So this one would still be a function. But that's not a function. Okay. All right, now equations are probably the hardest when you're brand new to this. Okay. I'm not really telling you what, giving you all the reasons that cause an equation to not be a function, but I'm giving you some things that definitely cause a problem. You can't have a y to the second or to the fourth or to the sixth. If you had y to the second equals x, if you tried to get the y by itself, remember how when you take the square root, you need to do plus or minus? So what happens is you might have an x value, say 4, that when you plug it in has two different y's matched up with it, 2 or -2, because of that plus or minus. So anytime you have a y raised to an even power, okay, you know for sure it's not a function, okay? Not a function. Okay, so that's a common one to look for. And you could have used that on this example I gave you up here. See how there's a y to the second power? Not a function, okay? There's other things that cause a relation to not be a function, like inequalities. You know how inequalities are like dashed or solid, and then you shade one side or the other? So you can imagine then you'd have a vertical line with a whole bunch of points. That means you have some x value that has a whole bunch of different y values. Okay, not a function. And then another case I put on here is x equals absolute value of y. See, if you thought about the graph of that, it's turned on its side, and so you would have a vertical line that would hit it in more than one spot. Just like x equals y squared is a parabola like that. It wouldn't pass the vertical line test. Okay, so sometimes I don't want to have to graph. I like to be able to use whatever representation they give me and determine whether something's a function. Okay, so you'll have a few questions about whether something's a function in the homework on function basics. Okay, now the next idea I want to introduce is the idea of domain and range. Okay, so right off the bat, I want you associating x with domain and y with range. So think of the x coordinates of all the points. So whatever relation you're looking at, you want to think about the x's of those points, and those would make up your domain, and the y's of those points would make up your range. Okay, so if you have a graph like we do, like let's just look at one of these. So if we look at this one, see that absolute value? If you think of that as a bunch of ordered pairs, if you could imagine what the x's of those ordered pairs are, all of the x's, that's your domain, and then the y's would be your range, okay? All right, so let's go ahead and fill in the notes on that. So the domain of a relation is the set of all possible x's. And if you have a graph, you're seeing the picture of all the possible x's. They're there in front of you. Okay, with an equation, you don't automatically have those in front of you. You have to think about it. Okay, and then by possible, here's what we mean. We mean any real number. Remember, real numbers can be nice, like 0 and 2, but they can be fractional, they can be negative, they can be decimals. They also can be pretty bad, like square root of 2 or square root of 21. Okay, they can be rational or irrational. They're just not imaginary. So for possible, we mean any real number for x that results in a real number for y. Okay. All right, and then the range just happens. You take the domain, you use your rule, and you get the y values, and all those y values would be the range. Okay. All right, now, there's only a handful of functions with domain issues. The two that we've experienced in our coursework so far from like Math 98 to now would be rational functions like this or radical functions like that. Okay, so we're going to look at those two situations. All right, so rational functions, the issue there, you might even be able to tell when you look at this, the issue there is you have a fraction and you have a denominator. And so, for instance, on this one, x better not turn out to be -5. Because if I put a -5 in for that x, I'm going to have 3 divided by 0. And you can't have a 0 in the denominator because division by 0 is undefined. Okay, so with rational functions, the domain is found by looking for what makes the denominator 0 and then excluding those values. Okay, so here's the domain. One way to say it is just to say x can't be -5. Okay, what's assumed is that you're saying what that kind of means is any real number except -5. All right, but a lot of times domains are written using interval notation. So if we want all real numbers except -5, it's like we want to say anything from here, just jump over -5 and keep going is okay. So interval notation does that. So -infinity to -5, go to the other side and keep going. And the parentheses we're using on the -5 are what make it exclude the -5. Okay, so that's another way of saying all reals except -5. And this right here is a common way we do domain. It's called interval notation. And so you use a parenthesis when you don't want it included and a bracket if you do. All right. Now, radical functions have a different issue. Okay, you can imagine on this one. Let's think about some ordered pairs on this. If I were to plug in 4, I would get square root of 4 minus 4, square root of 0, which equals 0. It works. It's perfectly fine to do that. Okay, and if I pick a 5, it works just fine. I get 5 minus 1, 5 minus 4, which is square root of 1, and that would be 1. I get a real number. So I'm putting a real number in and I'm getting a real number out. And 6, 7, 8 would work in the similar way. But look, if I put a 3 in, I'm going to get square root of 3 minus 4, and I'll have a negative under the radical, and this is imaginary. It's not real. So the domain is any real number you plug in, so 4 and 5, that give you a real number out, like they did here, a 0 and a 1. 4 and 5 are part of the domain, but 3 isn't. 3 was a real number that we put in, but we did not get a real number out. So it's got to be excluded from the domain. Okay, the critical value is the 4. Can you kind of think about that? 4 works, so did 5, so would 6, 7, 8. All of those are okay. 4 itself is okay. But if you go just a smidgen to the left of 4, like 3.9, you're going to have a negative underneath the radical. So you can't have that. So that picture that you see right there shows the domain. The domain would be all x is bigger than or equal to 4. You're saying all real numbers greater than or equal to 4. That's what you're really saying. And if you wrote that in interval notation, look at the graph to help you. It would be from 4 to infinity, including the 4. So I use a bracket to tell somebody I'm including the 4. Okay? So the deal is with radical functions, if you have an even root, there's a chance you might get this to happen. You might get an imaginary number. Okay? So functions involving even roots like square roots, you can't have a negative number under the radical, since that would cause the output to be imaginary, which is not real, which is not a real number, and so it can't be graphed in a real number coordinate plane. So, the graph for this in two variables would be from 4 over. It would look like that, okay? And so it doesn't go, there's no points to the left of 4. The graph kind of makes it explicit. If you just have the equation, you have to think it through. All right, so the big thing there to start with is that domain is x's, range is y's. Okay, keep that in mind. And then to understand some of the issues. There's only a few functions with issues, like linear functions, most linear functions, parabolas, polynomials, exponentials. The domain for a lot of functions is just going to be all real numbers. Any real number you plug in works. It's just ones like this have issues, like rational functions. There's gaps in the graph. Okay, so you're going to have a domain that's not necessarily all real number. The problem is if you have a rational function, you have a denominator, and that can't be 0. Okay, and then the other kind of function that has issues is a radical, especially a square root, because you don't want this right here. You need x minus 4 to be bigger than 0. You can't get a negative, bigger than or equal to 0. You don't want it to be negative or less than 0. In fact, you could do that to find the domain. You could just say x minus 4 has to be bigger than or equal to 0. And notice we would have gotten the domain. All right, now I don't want you to think those are the only two issues, but seriously, most functions have a domain that's all real numbers. It's just these are two cases. And then later in this course, we deal with logarithmic functions, and those have domain issues. Your domain has to be x's that make the input 0, that make the input bigger than 0. You can't have a 0 or a negative number. And then when you take trig, there's other ones too, like tangent, cosecant, and secant have domain issues. And when you have functions that have domain issues, that's why when you wind up dealing with equations that are based on these functions, you have to check them. You might do the algebraic process correctly, but the answers would have to be checked because they might turn out to be extra or extraneous solutions. Okay? Okay, now, the last thing in the basics I wanted to look at is really important. So I think I'm going to stop here in this video, and then I'm going to start my next video with this portion of it, and then we'll be doing some more examples on function notation, okay? So I'm going to stop